Okay, let's prove this lemma that we quoted a while ago, that Z and Fx are PIDs. Remind you, what that means is that every ideal in these commutative rings are principal, meaning that every ideal just looks like multiples of a single element. For example, the ideals in Z are all of the form A times C. By that I mean the set 0, A, 2A, minus A, etc. For some A in Z, I could say, but of course if you take minus 3 here and 3 here, you'll get the same thing. All multiples of minus 3 is the same as all multiples of 3, so I could just say non-negative integers. Okay. So these are all the ideals. We also saw last time this exercise that a priori you might have some ideals that do not look like this. For example, you could look at the ideal, I don't know, generated by 12 and 18, which amounts to looking at all multiples of 12 plus all multiples of 18, all things like this. I guess I wrote R1 and R2, where R1, R2 are arbitrary integers, but this set just happens to be all multiples of 6. So it's really just the ideal generated by 6. We don't write angle bracket in this case, we somehow write round bracket because the book does. So it just means all multiples of 6. And this comes from the properties of GCD. Okay, so let's do the proof for Z. The proof for Fx is similar. F, by the way, should remind you that means any field here. Okay. For Z. The zero ideal, meaning this guy, is certainly principal. It's generated by anything generated by 0 is certainly principal. There's nothing to do there. So let's take a non-zero ideal. Meaning, I'll remind you, ideal here means two-sided ideal. There is no left and right because Z is commutative. What it means is that I is closed under addition, multiplication, contains 0, but more. If you take any element of I and multiply by any integer whatsoever, it's still going to land in I. That's the key property. Okay? So you are given this ideal I, and what you're trying to show is that I just consists of all multiples of a single number. Where do you find this number? You might have seen such an argument before in chapter 2 when we were talking about divisibility, and GCD and stuff. So I claim that if you just take the smallest positive integer in I, the claim is that I equal to all multiples of M. I think I'm gonna call it, what's in my notes? Let's see. All multiples of B, where B is the smallest positive, strictly positive integer in I. And that's not an unreasonable guess, if you remember what we did in chapter 1. To know that there is a smallest positive integer in I just need to know there is some positive integer in I. But you see, I is non-zero. I don't want to write a whole bunch. This is written out in your notes. See, I is non-zero. So let's do some scratch work here on the right-hand side. I is not the zero ideal. So there exists some non-zero element in I. Now if m is in I, then so is minus m. And one of these guys is certainly strictly positive because neither of them is zero. So I does contain a positive integer. And if you look at all the positive integers in I, among them there is a smallest one. And this exists due to the well ordering. You can take all the positive numbers in I and take the smallest guy. Okay? And my claim is that I now consists of exactly all the multiples of B. And how do I go about this? Well, take anything in I. Any element in I. I want to show that A is a multiple of B. And we talked enough about divisibility that it should be almost a reflex at this point. You say, well, we just divide A by B anyway and see what happens. So by division with remainders, we can write let's divide A by B. I get a quotient and a remainder where Q and R are integers, and the key point is that the remainder is non-negative and strictly less than B. But now notice, here is the crux. Note that this R is A minus an integer times B. So it's A plus minus Q times B. And because A and B are both in the ideal, B by definition is the smallest positive integer in the ideal. So this combination is still in I. But R is strictly less than B. And B was the smallest positive integer in I. So what happens? R has to be 0. And R is strictly less than B. Since B is the smallest positive integer in I by choice, we must have R equal to 0. It cannot be strictly positive, then it would be an even smaller positive number which is still in I. So R is 0 means A is Q times B. So A is a multiple of B, so it's in B times Z, which we also write angle bracket B. That shows that every element of the ideal is actually a multiple of B. But if B is in the ideal, all multiples of B is also in the ideal. Conversely, B in I implies all multiples of B is also in I. I don't know why I use this notation. Let's just write BZ. That's better. But that proves both inclusions. Okay.